Alrighty, as promised, we'll now learn about negative exponents. So with negative exponents, let's refresh our memory on how we got them. So they came around because we did some kind of division problem, division of exponents, where the denominator had a higher power than the numerator. So let's take a quick look. Like, say we had x squared over x to the fifth. Our rules of division say that we should keep the base the same and subtract the exponent. So 2 minus 5 is negative 3. So x to the negative 3 would be the result, which has a negative exponent. So let's try to understand what this actually means in terms of the original problem. We said that we could always have rewritten the original problem the long way by following the basic definition of exponents. So in the numerator, x squared would be x times x, and in the denominator, x to the fifth would be x times x 5 times. So we draw in all those x's. And now we could cancel out 2 of them from the top and 2 of them from the bottom. So in the numerator, you could think of this as x times 1. So in the numerator we have a 1, all the x's are gone, and in the denominator we have x to the third power. So this x to the negative 3 has to be equal to this 1 over x cubed. So according to all the rules of exponents that we've done so far, both of these are valid ways to solve the problem, and so both of them must lead to the same final result. So even though they look different, here we have x to the negative power, and here we have 1 divided by x to a positive power, these two have to be the same. And so you could do this with many, many different examples, and you'll always get the same thing. A negative exponent always equals the same thing in the denominator with a positive exponent. So the rule that we can therefore write is x to the negative a equals 1 divided by x to the a. So when you have an exponent, a positive exponent tells you how many times to multiply by that number, and a negative exponent tells you how many times to divide by that number. So it kind of should make sense that positives pair with multiplication and negatives pair with division. So positive exponent tells you how many times to multiply, negative exponent tells you how many times to divide. Now, on the other hand, what if you have a negative exponent in the denominator? Okay, what happens when you divide by a fraction? Dividing by a fraction is the same as multiplying by the reciprocal. So if you have in the denominator x to the negative power, so say you have a negative exponent in the denominator, that's the same as 1 over 1 over. So you're dividing by a fraction, you flip it over and you put it in the numerator as a positive exponent. So if you have a negative, move it to the denominator. If you have a negative in the denominator, move it up into the numerator. So the negative sign just means kind of flip it from the bottom to the top or from the top to the bottom. And every time you flip it, you always, of course, change the sign. Okay, let's take some more examples here. And I also want to show you what to do when you have numerical values as well. So what if we have 3x squared over x to the 6th? Okay, we can write this as 3, there's nothing in the denominator to cancel it with, so we still have a 3. Then we have x squared over x to the 6th, so then we subtract the exponents. 2 minus 6 is negative 4. Okay, now here's where a lot of students make a big mistake. They see this negative exponent, and so they move the entire thing down to the denominator. But you have to remember, this 3 here, it has its own exponent, which is positive 1. So the 3 does not move anywhere. It stays in the numerator. Only the x to the 4th moves down. Okay, and another way to visualize this is with the zombie wars or the soldier wars. The 3 in the top, it's in the numerator in the original problem, so it has to stay in the numerator in the final answer. There's no reason for it to move to the denominator. Then we look at our x's here. We've got 2 in the top and 6 in the bottom. So the bottom has more. It's going to win by 4. So we have x to the 4th left over in the denominator. Let's keep going with another example. Say we have 16 a cubed b to the negative 4th over 8 ab squared. Okay, let's take a look. 16 divided by 8 is 2. A to the 3rd divided by a. Remember, this a has a 1 as its exponent if there's nothing written there. So a cubed over a to the 1st power. We subtract the exponents. 3 minus 1 is 2. And now with the b's, there's 2 different ways you could visualize this problem. Okay, the first option that you have is just following the rules of exponents. So if we did that, we would get b to the negative 4th divided by b squared. So when you divide, you subtract the exponent. So negative 4 minus 2 is negative 6. And then from here we can say, okay, I have a negative exponent. And typically, I haven't said this yet, but typically your answer should not contain any negative exponents. So when you think you have your final answer, check it, and if you have any negative exponents, move them to the other side of the fraction. So the 2 stays in the top, the a squared stays in the top, but this b to the negative 6th needs to move down into the denominator and become b to the positive 6th. We move it down because the negative means divide. So move it down, and now it's proper division. Okay. The other way you could have visualized this problem was, after you got your 2 and your a squared, when you're just looking here, this b squared, it's a positive exponent, so it can stay in the denominator. It's in the right place. This b to the negative 4th, because it has a negative exponent, it's kind of in the wrong place, so to speak, and you need to move it down into the denominator. So this b to the negative 4th, if you want to visualize moving it into the denominator, if you already had 2 soldiers here, and you added 4 more of them, now you have 6. So you have b to the 6th power in the denominator, and that kind of gets you straight to the answer, skipping this one step here in the middle. So whichever way you like to visualize it, you could use the rules of exponents when you're dividing to subtract and get a negative number, and then apply the negative exponent rules to move it to the denominator. Or you could try that first and see what you get. Remember that you always want to have positive exponents in your final answer, but it doesn't matter along the way if you have negatives as you're simplifying it. Okay, let's take a look at one more kind of possibility here. What happens, well, let's go to the next slide. Okay, so 0 in the exponent. So this is a continuation of this same video. So what happens when you get a 0 exponent? So since we've learned our rules of division, what if we have x to the 3rd over x to the 3rd? Well, the rules of exponents and division say that we should subtract these two, which is x to the 3 minus 3, which is x to the 0. Okay, but we know that anytime you divide something by itself, what's always the answer? Like 5 divided by 5, or 17 divided by 17. Anytime you divide by yourself, you always get 1 as your answer. So because we can use the rule of division to write that as x to the 0, but we know the answer has to be 1, we can conclude, therefore, that anything to the 0 power has to equal 1. Let's look at another example. Let me say, as long as x itself is not 0. As long as x is not equal to 0. So any whole number or any fraction or any decimal to the 0 power is 1. But the reason x can't be 0 is because we're dividing by x cubed. So if x itself was 0, we would be dividing by 0, which we've learned you can't do. So as long as x itself is not 0, raising it to the 0 power equals 1. Okay, so let's do one more example here. Let's do something like this. X cubed times y squared times y to the negative 2 equals what? Okay, well, x cubed, there's no other x's anywhere, so we can just write that, x cubed. Then here we have y squared times y to the negative 2. The rules of multiplication say that we should add the exponents, which gives us y to the 0. Okay, but we don't need to write this y to the 0 because it's just equal to 1. So this is just x cubed as our final answer. Alternatively, we could have visualized this by saying this y to the negative 2, because it has a negative exponent, that means we need to move it into the denominator, right? So really, it's like dividing by y squared, and the y squared and the y squared, they can cancel out, leaving us with just x cubed. So dividing, the rules of dividing exponents, where you subtract the bottom exponent from the top exponent, combined with the idea of negative exponents, where you move them from the top to the bottom, all plays into this idea of having a 0 exponent. Because oftentimes when you're canceling stuff out or subtracting, you end up with a 0, and you have to remember what to do with it. The last example, I think I have a new page here. Another example is, it doesn't matter how complicated the base of your problem is, as long as the exponent is 0, the overall answer is equal to 1. So you could have something nasty like ab squared c to the negative 2 over a cubed b to the 5th c to the negative 8th, and then you could have all of that raised to the 0 power. And you don't have to go through and figure out what's a over a cubed, what's b squared over b to the 5th, what's c to the negative 2 over c to the negative 8. All that stuff, because you notice, or hopefully you notice right away, that this whole thing is to the 0 power, then the answer has to be 1, regardless of what's inside of here. Okay, it doesn't matter how complicated or how simple the stuff inside the parentheses are. As long as you have a 0 exponent, your final answer is 1. And that's all there is to it.